Welcome everybody. Today we're going to be covering a bunch of things from mass spectroscopy to isotopic abundance to hydrates to empirical formulas and even molecular formulas and average atomic mass. So with that, I've been challenged to do this lesson as fast as I can. Let's get right into it. So right away, we're going to start with my tile whiteboard. Okay, we're going to look at oxygen, okay? Oxygen has a molar mass of 15.99. Now where does this decimal come from? Okay, so we know that the only thing that makes up a mass of a atom is protons and neutrons, but both of them masses are just 1 AMU. So where do we get decimals from? Well, we get decimals from variations called isotopes. Okay, you see, oxygen has a mass of 16. Okay, so since we are really close to 16, that means most oxygen, say for example 92%, has a mass of 16 AMU. Okay, but there's a very small percentage, 5%, which have a variation. Okay, so that 5% could have a mass of 15 AMU. Now it's that 5% that have a mass of 15 AMU. How do they have a mass of 15 AMU? Well, the protons can't change because then our atomic number would change. What can't change? The neutrons. So in this here, how many protons would you have? Well, you need to have 8 protons. Okay, but you would only have 7 neutrons. Okay, because 7 plus 8 is 15. Here you have 8 neutrons, 8 protons, right? Now there might be 2% that's even less, that's 14 AMU. Okay, and then there might be some that is 17 AMU. So you have a bunch of these variations, and these variations are called isotopes. Okay, isotopes, basically isotopes vary because of the neutrons. So more or less neutrons changes the mass, average mass. That's why these number, the given on the periodic table, is that average mass. Now how do we calculate this, and what are we looking at? Well, those percentages that I just showed you, well, those are abundance. Okay, so for oxygen, that abundance shows that 90, not 25, where did I get that from? It shows that 95% of oxygen is 16 AMU. Okay, so for this abundance, that means that most oxygen is at 16 AMU, right? Then we can say that 4% is at 15 AMU. Now these numbers are just made up here just for proof of theory, okay? So 15 AMU, that means that 4% of a billion would be 15 AMU, and 95% of that billion would be 16 AMU, and then we can say that 1% of that billion is actually 14 AMU. So now how would we calculate our average, right? We have to get into our average atomic mass. Well, our average atomic mass is a formula. So average atomic mass units, okay, is equal to the sum, okay, so this means the sum, that means you're adding, okay, it is the sum of our mass, okay, so our exact mass times abundance, okay, so abundance okay, so basically what this means that, so however many masses we have, so if we have 3 masses, we're going to do exact mass of say 95%. So for this example right here, what this equation would look like is actually, it would look like, I'm not going to write it because we have to quickly do this, it would look like 16 times 0.95 in brackets plus 15 times 0.04 plus 14 times 0.01. Add those all up, and that's how you get your atomic average mass. Okay, simple things. Okay, let's speed along, speed of light. Okay, next up, back over here, we have to deal with mass spec. Well, what is mass spec? Well, how did we find all of this out? I'm going to show you one easy way. We took a big magnet, okay? So we took a big magnet, okay? So this is our magnet, okay? Big magnet, okay? And what we did, we took a tube. And in this tube, we took some atoms, okay? We took some atoms and we fired them, okay? We fired them. And what happened was, well, these atoms, they all went in here. They went in fine, okay? But once that magnet rays hit, right, something cool started to happen. Well, you had splits within these rows. So okay, and then there was basically a paper here that scanned all of these hits, right? It scanned all of these hits hitting it, and it had identified something. Now, I know this is very rough, but basically what it saw was this magnet affected these draws, okay? It affected these strings. So if I look at something, and if I say I have water flowing this way, right? I have a string flowing this way, right? And now I'm sucking air. I'm creating vortex towards me. Air is going this way, okay? This is where our magnet is. Okay, as it goes, if I'm dropping multiple balls, okay, some heavy, some light, what's gonna happen? Well, when I'm blowing, well, the lighter balls are going to start coming this way. Okay, then the medium balls are going to be like this way, and then the heavy balls are this way, right? So if we draw out their paths, the lightest balls are affected the most and the heaviest balls are affected the least, right? Because they're lighter. That is what we found with this mass spectroscopy. Using this magnet and using a way to get all of this light here, the simple thing you need to understand is that this magnet affected these items. It basically separated them. It was able to move the lighter ones as close to it possible, making them follow this trajectory, while the heavier ones, they followed the regular trajectory because they were harder to move from this magnet. Same thing here. A different trajectory because it was lighter. And that right there is mass spec, a very, very simplified version indeed. If you do want details, please go and look at this, but that is the basic concept you need to understand for mass spec. Finally, we have 3 different formulas, okay? You need to know your molecular formula. Okay. There's your molecular formula, there's your empirical formula, and then there's your hydrate. Okay, starting with your molecular formula, this is just your regular formula that you see every day. So we're going to do C8 and H12. Okay, that's an example, okay? Another one is Na2SO4, right? These are just molecular formulas. They're just regular full formulas, okay? Now, we're going to keep using this as an example. Okay, what's an empirical formula? Well, molecular formula is a specific formula to a specific compound. An empirical formula is basically that ratio. So if I divided these, right, what's the common divisor I can get? Well, 4 is one of them, right, and so is 2. So I would actually divide both by 4. So my empirical formula would be C2H3. Okay, this is the base ratio. Right? With this base ratio, with this base empirical formula, multiple molecular formulas can be created, including one of these, right? So the hierarchy is empirical formula at the top, which makes multiple molecular formulas, okay? Makes multiple molecular formulas, okay? So again, this can make C4H6, right? It can make C8H12. This can make, multiplied by 8, it can make C16H24. Many of them. Finally, we have hydrates. What are hydrates? Well, hydrates are, pretend we have our CuSO4, our copper 2 sulfate, right? Those crystals were actually hydrates. Hydrates basically just mean that the actual crystal, the crystals, or like whatever the solid are, they are actually bonded with water. Okay, they're not just aqueous. They're not aqueous products. They're actually bonded with water. Water is a part of their system. An example of this could be, say we have Na here, right? O, and then H is legitimately an integral part of this. Right now, this is just what happens in water, but now pretend this structure existed outside. If I took this out of water and this was a physical part of it, that right there would be a hydrate, and this would just be Na. We put a dot, right, and then we put 4, however many hydrogen molecules we have. Okay, and that right there, I covered everything.